On Wednesday and Friday of last week, we looked at the photoelectric effect. The photoelectric effect essentially says this. When light strikes a metal, sometimes an electron is ejected. When is an electron ejected versus when is an electron not ejected? Who can give me the answer to that question? When is an electron ejected? Yep. When what's above the threshold frequency? When what's above the threshold frequency? Good. When the EMR that strikes the metal or whatever other material is above a certain frequency called the threshold frequency. Now, prior to 1905, when Einstein came along and explained this really well, everybody thought that we needed more energy to get an electron ejected, we get more light. Well, that didn't work. More light didn't work. If a certain color of light didn't cause photoemission, then it didn't matter how much of that color you had, you would never get electrons ejected. So what do? We ended up increasing the frequency. But it wasn't until Einstein in 1905 that explained why increasing the frequency would cause electrons to be ejected. Einstein said that energy is equal to h times f. That's the energy of a photon. The energy of a photon. A photon is defined as a what? Sometimes we call it a particle of light. A better definition is a quantum of energy. Okay, each little bundle of energy, each little particle of light has an energy equal to h times f or hc over lambda. If we have more frequency, then we have more energy. If we have more energy, then it increases the probability of an electron being ejected. Now, if the light, the EMR, is above the threshold frequency, we always say that it's a 1-to-1 ratio. So 1 photon will cause 1 electron. 1,000 photons will cause 1,000 electrons if you're above the threshold frequency. If you're below, then 1,000 photons will cause what? Nothing. Zero electrons emitted, right? All right. What if you're way above the threshold frequency? If you're barely above, then 1 photon will cause 1 electron. 1,000 photons will cause 1,000 electrons. What if you're way above the threshold frequency? How many electrons does 1 photon cause now? 1. How many electrons does 1,000 photons cause now? 1,000. So the number of electrons ejected has isn't affected whatsoever by the frequency of the photon, except that it has to be above a certain value. Okay? So what's the difference then? What if you shine gamma rays on this metal when ultraviolet would cause the electrons to be ejected? What's the difference if it's the same number of photons? Good. The electrons ejected would have a higher energy with gamma rays because the photon has a higher energy, and of course the energy has to go somewhere, right? Make sense? All right. We defined a couple of terms, the threshold frequency. We kind of already talked about that, right? The minimum frequency necessary to eject the electron. Corresponding to the threshold frequency is the threshold wavelength. What's the symbol we give to threshold wavelength? Lambda max. Because if you have a min frequency, you're going to have a max wavelength. The next term was the work function. If frequency was the minimum, sorry, threshold frequency was the min frequency necessary to eject the electron, then work function is the minimum energy necessary to eject the electron. Anything below that, nothing happens. Anything above that, 1-to-1 ratio. The energy of a photon was h times f. The minimum energy would be h times FO, the minimum frequency. But it would also be equal to hc over lambda max. This part of the equation is on your data sheet. The last part is not. Okay. Then we talked about the stopping potential. The stopping potential. Sometimes they call it the stopping voltage. The potential difference that's required to stop an electron once it's already been ejected. So the photoelectric effect has already taken place. Now we're stopping that electron. We're almost not reversing it because we're not putting the electron back, but we're stopping it. We're not letting it go any further. We're not letting it reach a collector and form some kind of complete circuit here. We're stopping the electron. This is the potential difference that's required to stop that electron dead in its tracks. It's related to the kinetic energy. The kinetic energy of what? If something's going to have kinetic energy here, what is it exactly that's going to have the kinetic energy? The electron, right? The electron's the thing with mass that's moving. It's going to have the kinetic energy. How is the stopping potential related to the kinetic energy of the electron? No, not the inverse. multiply by the charge. We can say that the kinetic energy of the electron is going to be 1/2 mv squared. Well, we'll say 1/2 mv max squared because we're talking about the max kinetic energy of the electron. But it's also equal to, as Mac just said, Q times the stopping voltage. What Q would we use there? 1.6 times 10 to the minus 19 because it's an electron that's ejected, right? This is on your data sheet, although it looks slightly different. It doesn't say EK max is equal to 1/2 mv squared. Under your energy section, it just says EK is equal to 1/2 mv squared. EK is equal to QV stop is also on your data sheet, but they appear in different places. Nowhere does it say 1/2 mv squared equals QV stop. They're both there. You just got to know where to find them. That's all. Does that make sense? All right. We had some homework over the weekend. We worked on 3 sets of questions on Friday. The questions that we worked on were 716, 718, and 719. Okay. We haven't had a chance to look at anything from 719, so I suspect we'll have to look at something there. Is there any other questions besides 719 that we need to go over? 716 or 718 on either of those pages? Okay. What about 719? The last set of questions that we didn't look at all on Friday, we just kind of assigned. Yep. Number 2. Okay. Any others? Yep, absolutely. Number 1 and number 2. 3 is okay? All right. Number 1 says a photoelectron. A photoelectron is just an electron that has been ejected from the surface. Okay, so the photoelectric effect has taken place. It's emitted with a kinetic energy of 2.1 electron volts. So that's going to be the max kinetic energy of the electron. Note that it's in electron volts. Maybe we can leave it there. Maybe we can't. How fast is the electron moving? Let's go back to our equations that we have that are valid here for the photoelectric effect and see which one seems to fit the best here. Kinetic energy of the electron. How fast is it moving? What are you going to use here? What do you want to try? Sorry? Let's try 1/2 mv squared, right? Again, you're not going to find that equation under this unit. You're going to find this equation way back under energy, okay? But in the end, we all know the kinetic energy is 1/2 mv squared anyways. Good question. There are certain times when energy has to be in joules. Most times, it doesn't matter whether you're in joules or electron volts. When are the 2 times that we've learned so far that we must be in joules? Good. If you're using 1/2 mv squared or Q times V, you can be sure that if you have a test question involving kinetic energy, that there's going to be 2 answers. One is going to be based on you using joules. One is going to be based on using electron volts. You need to use joules here. When you're using QV or 1/2 mv squared, you've got to use joules. So we got 2.1 electron volts. Let's do the conversion there first. 1 electron volt over 1.6 times 10 to the minus 19 joules equals 2.1 electron volts over x joules. The x goes up, the 1.6 goes up. X ends up being 1.6 times 2.1. What do we get for that for the energy there in joules? 3.36 times 10 to the minus 19. Thank you, Brendan. Okay, so now we're going to plug this in here. Solve for speed, by the way. It becomes 2ek over m, square root that. 2 times 3.36 times 10 to the minus 19 over the mass. What mass do we use? The only thing involved in the photoelectric effect that has a mass is the electron. So we've got to use the mass of the electron. The photon doesn't have any mass. Can't be that. You do the math there, and I think we should get 8.6 times 10 to the 5 meters per second. Now, the good news is, if you forgot to convert to joules here, and you use the electron volts for the kinetic energy, I'm not sure what you would have gotten for the speed, but it would have been an unrealistic speed. So although that option probably would have been there on a multiple choice question, if you do that and you get that speed, you should be able to look at it and say, wait a second, this doesn't make any sense. I must have made a mistake. Okay. 2.1 times 10 to the 15, okay, which clearly is wrong because it's It's about, about 10 million times the maximum speed of an electron, right? All right? So let's not rely on that, because maybe you don't notice that. Okay, but at least it's a little check that might tell you that you made a mistake there. So is that good? Who asked for one? It's good? All right, let's take a look at number 2 then. We'll kind of do 2 and 3 together, actually, because they kind of go together there. 2 says, what's the kinetic energy of a photoelectron emitted from a cesium surface when the surface is illuminated with 400 nanometer light? This is going to be the wavelength. Now, be careful here, okay? People get confused between lambda and lambda max, frequency and minimum frequency, the threshold frequency. How do we know the difference? How do we know that this is not lambda max? This is just lambda. Well, here's the rule. It's in the end, it's quite simple. If it doesn't tell you it's the maximum frequency, the threshold frequency, the minimum frequency, the threshold frequency, or the max wavelength, the threshold wavelength, if it doesn't tell you, then it's not. If it just says, here's a wavelength, then it's got to be just a wavelength, not a threshold. Okay? Now, if it does say the maximum wavelength, or again, threshold wavelength, something like that, then make it lambda max. Otherwise, just make it lambda here. We want to find the kinetic energy of this electron. I can't think of an equation off the top of my head, a simple equation that has both lambda and EK max in it. Can you guys think of where to start with this? Sorry? Okay, so let's say HF is equal to EK max. What's the work function? Where does that come from again? What law does this stem from? Conservation of energy, right? The initial energy equals the initial energy of the photon equals the final energy of the electron plus whatever we used up in the process, the work function. All right, we don't have frequency, but we do have lambda, so let's replace HF with HC over lambda. EK, we'll just leave that, EK plus the work function here. Now, the work function for cesium is found on one of the tables that we saw on Friday, and I can't remember what the table number was. 14.1. Okay. What was the work function for cesium? 2.1 electron volts. You're never going to need to remember that number, right? I don't remember that number. Okay, and I've seen this question, I don't know how many times, a bunch. I don't remember the work function of cesium. Okay, you don't need to remember that. Now, in all likelihood, it's not going to be given to you in a table. In all likelihood, you'll have a half or a full page of information with that number buried in it somewhere. Okay, find it and then use it. By the way, can we stick with the electron volts here, or do we have to convert to joules? Well, yeah, it depends on what H constant you use. If we use the 4.14 value, the electron volt seconds, can we stick with the electron volts here? Yes, yes, we can. Although we're solving for kinetic energy, nowhere yet have we introduced 1 FMV squared or QV stop. Make sense? Okay, now we can go to joules. If you're confused about that, let's just use joules. Convert it and go with that. But if you want to save yourself a little bit of time, in this question, you can stick with the electron volts. Let's go 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by lambda. Don't forget to do the nanometers in that. 400 times 10 to the minus 9 meters. So get that number, take the 2.1 over by subtracting, and we should get, for a max kinetic energy of this ejected electron, 1.01 electron volts. Okay? Had you converted that to joules and used 6.63 value for H, you would have gotten a number that was somewhere around 1.62-ish, 1.61 times 10 to the minus 19 joules. That would be absolutely correct. Now, be prepared on a test to be asked for the answer in electron volts. So even if you do it in joules, you may have to convert back to electron volts. That's okay. It's just an extra step, that's all. Hey, now question 3 asks us for the max speed. We could have been asked for the maximum speed here. See, we could have combined 2 and 3 right away. We could have replaced EK with 1 FMV squared and solved for speed. What would we have had to do if we did replace EK with 1/2 mv squared? How would this question have changed? We would have had to convert to joules then, right? We would have had to be in joules. Now, as it stands, okay, we calculated the kinetic energy, and that's fine to stick with that in electron volts. But now that we're going to do now that we're going to do speed, now we have to go back to joules. So we're going to say V is equal to 2 EK over M. The kinetic energy, right, 1 electron volt over 1.6 times 10 to the minus 19 joules equals X equals 1.01 electron volts over X joules. X was, what did you guys say, 1.61? 6125 times 10 to the minus 19 joules. Okay, plug it in here. Okay, solve for speed. And we get 10 to the 5 meters. 5.95 times 10 to the 5. There's been a lot of times this year where we've said, you get a number that's kind of in this range, you got a pretty good chance that you're right? If you're outside of this range, then there's a pretty good chance that you're wrong. Now, it's hard to remember all of those things, right? Okay. Bottom line is, look, if you did something wrong, you used electron volts, or you messed up on this, you're getting a number for speed. I don't know what it's going to be, but it isn't going to be anywhere close to the value that it should be. And look, when you're talking about the speed of an electron, it's almost always going to be that 10 to the 5, 10 to the 6 range. It could be slower. It could even be faster a little bit, but it's usually going to be in that 10 to the 5, 10 to the 6 range. So if you're way off of this, okay, give it some thought. Okay, try again. Okay, and the most likely mistake that you make in questions like this, or a lot of the questions we've done this year, are those silly mistakes of conversions or something like that, right? Or forgetting to square root or something like that, right? Got it? You guys feel pretty good about this? All right, I got a picture up on the board here. It's of a very rudimentary burglar alarm here. I want you to take a look at this picture for a second. Again, I want you to take maybe about 1 minute. See if you can kind of work through it and see if you can figure out how exactly this thing works. Okay, and then in a minute, we'll ask somebody to explain it to me. If you can't do that, then I'll explain it for you, okay? Anybody have an answer for this? Does anybody think they know how this thing works? Travis? Okay, so when a light's not touching it or hitting it, it turns on a magnet. Okay, yeah, you're kind of right. We probably need a little bit more detail than that, but yeah. Okay, stop right there. We'll come back to you in just a second, okay? Let's go one step at a time, though. Okay, Colton's right on the first step. He says the UV light must be above the threshold frequency, right? Okay, if it's below the threshold frequency, all bets are off on this. If it's above the threshold frequency, the UV light strikes the sodium cathode, and what happens at the sodium cathode? The electrons are ejected, right? So what happens, Colton, to that electron? Or to those electrons, I should say? Good. So you got an electric current now that's flowing. It's flowing through this piece of steel here, okay? And it goes around here. Well, it's not flowing through that piece of steel. It's flowing through the wire that's wrapped around that piece of steel. And it creates a what? A magnetic field, right? So it becomes an electromagnet. We could, if we wanted to, find out the polarity of that, right? Using the stuff that we learned in our magnetism unit. So we got an electromagnet, right? Go ahead, Colton. Okay, so this is an iron switch, a ferromagnetic switch. When we've got a magnet right here, okay, because the current's flowing through the wire, it attracts that iron switch and it holds it there. Good. It pulls this string, right, or this spring, sorry, stretches that spring, okay, but it's a stronger force. The spring can't pull it back because the magnetic force that's attracting the iron switch to it is too strong. Okay, good. Okay, hold on for a second. Hold on for a second. You skipped a step there. Okay, right now this iron switch is touching This electromagnetic with the soft iron core, right? Okay, right now, we do not have a complete circuit here. If we don't have a complete circuit here, what happens to this alarm? Nothing. Doesn't go off, right? So the alarm just sits there. Okay, now go ahead again. Okay, so this guy breaks the light beam. Okay, so now the light beam is not striking the sodium cathode. Now there is, good. Good, excellent, excellent. So there's no electrons being ejected here because there's no light above the threshold frequency causing the electrons to be ejected. There's no current going through here. Okay, there's no electromagnet. If there's no electromagnet, then the spring that was stretched is just going to pull that iron switch back. Now that iron switch is now in contact with the contact. That forms a complete circuit. Now there's a current going through there. Okay, what happens to the alarm? The alarm goes off, right? Now this is pretty simple example of a circuit, or a pretty simple example of a burglar alarm, because what happens when the guy steps out of the path of the UV light here? It stops, right? Okay, you'd have to have some mechanism for the alarm to keep going, right? But this is a basic example of the burglar alarm. We'd have to just add some stuff to it, some kind of permanent switch to it that would allow, even once he stepped out, for this to keep going. Maybe there's some kind of lock down here that locks it in place, something like that. Kind of like a circuit breaker. You guys know how a circuit breaker works, right? There's a bimetallic strip in it. When it gets hot, it bends, and then what happens? It locks in place. So even after it cools down, it doesn't go back, right? What do you got to do? You got to flip the switch, right? Okay, which unlocks it basically and it lets it go back in place. So you'd probably have to have something like that in order to lock this iron switch in place until you flip the switch to let it go back. Okay, make sense? Good. Good. Have a look at this diagram on the board right now. This is an experiment that could be used to determine the stopping potential of the ejected electrons and therefore to determine ultimately the threshold frequency of the ejected electrons. Have a look at this. Okay, we've got incoming photons right here. Okay, these are our incident photons. This is F or lambda. Okay, this is not F minimum or threshold frequency or threshold wavelength. It's just the photons, okay? They're striking this metal surface right here, and they're causing electrons to be ejected. Now, we've got a power supply hooked up so that we've got a collection plate over here that's positive. What's that going to do to these electrons that have been ejected? This positive plate will do what to these electrons that have been ejected? It's going to attract them. So the electrons are going to go over here, right? And as they go over here, they're ultimately going to go around the circuit here, and they're going to form an electric current. That make sense? Now this ammeter is a device that measures electric current. As long as we've got it set up like this, then we have an electric current being measured, an electric current being detected. Okay, if these incoming photons are below the threshold frequency, well then we're not going to detect an electric current. But as long as they're above the threshold frequency, we'll get a value right here. We'll get a value measured there. Does that make sense? Okay. That's not exactly how we're going to determine the threshold frequency though. The stopping voltage and then the threshold frequency. Let's do this. Let's reverse the polarity here. Let's make this the negative plate and this the positive plate. We have incoming photons here. We can still get electrons ejected, right? We can still get electrons ejected from this positive plate. There's electrons in this metal. But what happens when these electrons are ejected? They're ejected with a certain kinetic energy going this way, but they're going towards the negative plate. What happens? They what? Well, they accelerate, but it's a negative acceleration. It's a deceleration, right? They slow down, and if the potential difference is high enough, they slow down and they stop, right? How do we know when they've stopped? We can't see these electrons. We can't physically look at them even under a microscope and see the electrons. How do we know when the electrons aren't moving anymore? Sorry? The ammeter doesn't measure anything, right? You get no electrons going around the circuit. You get no electric current. The ammeter measures 0. So whatever potential difference you needed to apply in order to cause the ammeter to read 0, that's your stopping potential. Now, What's the use of that? So you've got the stopping potential measured for this particular photon. This particular frequency of photon. Well, let's repeat it. Let's increase the frequency of the photon such that we're still above the threshold frequency, but it's a different frequency than we were at before. Let's see what the stopping voltage is for that. And again, and again, and again, and so on. What do you think we're going to do? Plot a graph. Now, there's a couple of graphs that you can plot. The first graph, and the more common graph, is not stopping potential versus frequency. Rather, it's kinetic energy versus frequency. How do you get kinetic energy from stopping potential? Multiply it by the charge, right? So it'd be Q times V stop. Just add another column to your table, right? Make sense? So the more common one that you see is this graph right here, max kinetic energy versus frequency. Now, what's the value in plotting this graph? Well, let's go back to the analysis that we've done quite a few times now with graphs. Straight line graph, what's the equation that describes it? Y equals mx plus b, every time, right? Okay, this is the equation from my graph. The y-axis is ek. M is the slope. The x-axis is the frequency. Is there a y-intercept here? Yes, there is. So we can't get rid of b there. Okay, I'm sorry? What's the equation now from our data sheet or from our heads that has both ek and frequency in it? HF is equal to ek max plus w. Let's do that in a different color here. So not exactly from our data sheet this time. Usually it is, but not exactly this time. But it's still an equation that comes mathematically as opposed to graphically. Okay, let's rearrange it to solve for ek. We get HF minus W. It's a cross off things that appear in both. EK disappears. F disappears. The slope is equal to what? Slope is equal to the constant. The y-intercept is equal to what? Negative work function. That make sense? So you want to find Planck's constant. Let's say it's just the slope. We want to find the work function. It's the negative of the y-intercept. Good? Well, we still haven't actually found the threshold frequency yet. See, this analysis doesn't give us the threshold frequency. But what you could do, there's a couple of options here. What you could do is say, well, W is equal to H times the threshold frequency, right? We just got W from the y-intercept. We just got H from the slope. Solve for the threshold frequency, right? But there's actually an easier way to find the threshold frequency here. The minimum frequency at which electrons are ejected. The x-intercept, yeah. Okay. Anything below that frequency, look at what happens. There's no kinetic energy of the electrons. It's given as a negative value, right? Anything above that threshold frequency, there's a positive kinetic energy of the electrons. In other words, they've been ejected. Make sense? That's not that hard, is it? Okay. Two things that I want you to take away from this. First of all, we see this graph quite often. Okay, we see this graph quite often. We need to remember how to find all three of these things from this graph. The second thing, though, is that, look, if you forget how to find them, can't you figure it out? How many times have we gone through this process now? Is that process of y equals mx plus b starting to make sense to you? We will get a question in a month's time. We will get a question where we have to analyze a graph in this way. There's a good chance that it'll be a graph you've never seen before. There's a good chance of that. There's maybe a 30 or 40% chance it'll be a graph that you've seen. Okay, a 60 or 70% chance it'll be a brand new graph. Okay? If you can go through this process that we've just gone through, and now that we've done it 7 or 8 times, you should be okay with that question. Let me tell you, by the way, the provincial average on that question last semester. I can't remember the exact number. It varies from year to year, but it was somewhere in the range of 10%. Somewhere in the range of 10%. So about 90% of the grade 12 kids in Alberta got this wrong. Honestly, I think that you guys are relatively well positioned to get that question right. Okay. Sometimes it's just that brutal question that it's like, holy cow. But most times, if you know how to do this analysis, you're in really good shape for that question, okay? We should be able to get 75% of us, not 10%. Yep. The graph will be a straight line. Yeah, it has to be a straight line. Now, there's analysis you can do if it's not a straight line, but you kind of have to make it into a straight line, and that'd be too much for you for a multiple choice question. Right? Hey, quick question. What if I gave you this here? What if I give you EK versus frequency? This is the last question on the page. Here's your graph. It doesn't give you anything below the y-axis. Okay, and your page is cut off right here. And I ask you to find the work function. How did you find the work function again from this graph? The y-intercept, right? Any suggestions? Okay. If you have clearly marked data points, yes. You can still do it on your calculator, and your calculator will spit out the y-intercept. Absolutely. Okay, option number one. Option number two, let x equal 0. Yeah, you'd have to have the equation, though, for that, right? Okay, that's a good thought, actually, but you have to have the equation given to you already for that. My thought was this, guys. Look, we can find Planck's constant by the slope, right? We can still find the slope of that graph, right? Okay, now, by the way, I'd suggest you use your calculator for that. Okay, and if you're going to use your calculator, Dallin suggested that maybe we just use your calculator to get the y-intercept. Okay, good idea. If you're going to use your calculator, you might as well get the y-intercept from the calculator anyways, right? Okay, but for whatever reason, you can't, whatever. Okay, what's another option? Well, the Planck's constant is the slope. The threshold frequency is the x-intercept. Well, that's pretty easy to get. You don't have to use your calculator for that. Just read it right there. How do you find the work function? Multiply them together, right? So the y-intercept will be the slope times the x-intercept. Does that make sense? You got a few options here, right? You got a few options depending upon the question. Good question. Does it matter what units you use for h? Well, it depends on what your answer needs to be in for work function, right? If your answer for the work function, it was 4 options in a multiple choice question, and they were all in electron volts, well, then h should be in electron volts. Generally, though, h here is going to be in whatever units you have kinetic energy in here, right? That makes sense? Because your axis is going to be either joules or electron volts. You're probably going to find h from that in the same units, and then you're probably going to find the work function in the same units still. I'd be surprised if you get a question where they gave you joules for the y-axis and asked for the work function in electron volts. It's possible, but I'd be surprised. Just do the conversion in the end if you have to. Remember, Tanner, if in doubt, go with joules, right? Okay. Okay, let's do a couple multiple choice questions. Just in the interest of time here, guys, just we'll just kind of do them together here, okay? First one says, photoelectrons are emitted when blue light of frequency 6.4 times 10 to the 14 shines on a metal surface. Hey, this is a frequency, right? 6.40 times 10 to the 14. Is that just a frequency, or is it the minimum frequency, the threshold frequency? Sorry? Just a frequency? What did you say? Minimum frequency? Which is it, guys? We got 2 people fighting over here. Well, not fighting. I'm kind of creating that conflict, but 2 people disagreeing. One person says it's just a frequency. The other person says it's the minimum frequency. Blue light of this frequency shines on the metal. Doesn't tell me anything about minimum, right? Doesn't tell me anything about threshold. Doesn't tell me anything about electrons barely being ejected. Okay, so this is going to be frequency, right? Not F0. Yeah, it doesn't say that, right? Well, yeah, yeah, no, it does. I see what you're saying there, actually, yeah. Photoelectrons are emitted when blue light of frequency, blah, 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 shines on this surface. But it doesn't, I don't think that it's inferring that it requires blue light. Right? It could just easily say photoelectrons are emitted when ultraviolet light shines on it, because they are, right? Maybe red light would cause it as well. It just doesn't say that. So I see where you're coming from on that. But stopping voltage or stopping potential, 1.25 volts. What's the maximum kinetic energy? In the end, okay, the debate that we're just having about the frequency versus threshold frequency, I don't think is going to really matter. But we still want to be able to identify that, because sometimes it is going to matter. You want to find the max kinetic energy? Let's just go EK is equal to QV stop, right? Now, unfortunately, I see kinetic energy all given as 10 to the minus 19 joules. Yeah, I was kind of looking forward to maybe doing this question, being able to eliminate a couple possibilities right away. I can't, because they're all 10 to the minus 19. When you multiply this by the stopping potential, what do you end up getting? 2 times 10 to the minus 19. Okay. Relatively straightforward question, right? We can do that. Right? We can do that question. Well, 119. The threshold frequency of light for the emission of photoelectrons is 4.4 times 10 to the 14. Logan, which one's this? Is this F or F0? This is F0, right? It tells me it's the threshold frequency, the min frequency. If light of frequency 6.6 times 10 to the 14, what's that one, Logan? Mac? 6.6, is that F or F0? It's going to be F. It's higher than F0, it's going to be F. Shines in the middle of the max kinetic energy, we're looking for EK max. You got 5 seconds to come up with an equation here. 1, 2, okay. If you can't come up with it in 5 seconds, go with the one that it's almost certainly going to be. HF is equal to EK max plus W, okay? Our answers are all in joules, so we're going to use joules here. 6.63 times 10 to the minus 34 times 6.6 times 10 to the 14 equals EK max plus the work function. Work function is going to be Planck's constant times the threshold frequency. I almost just made a mistake here that I wonder if some of the rest of you might make too. I was going 6.63 times 10 to the minus 34 times 4.14 times 10 to the 14. Why did I do that? It's wrong, obviously, right? Sorry? It's a pretty familiar number, right? In this context even, right? Photoelectric effect is a pretty familiar number, so watch things like that. That's kind of mean, actually, that they gave us that number. Because I'm guessing of 8,000 students in the province every semester that write this exam, I'm probably not the only person that's, you know, when your mind isn't quite thinking clearly, making that mistake. And what do we end up getting there, guys? C, 2.9 times 10 to the minus 19. Again, nothing that kind of jumps out at me as being D. D. Oh, wow, Tanner, that's embarrassing, isn't it? 1.5 times 10 to the minus 19. Just double check that, Tanner. Oh, here's a good one. On a movie film, the soundtrack is located alongside of the film strip and consists of light and dark regions. So here's the film strip, and you can see here, right here, in the soundtrack, the light and the dark regions. Light from the projector is directed through the soundtrack onto a phototube. The phototube is basically a photoelectric detector. Variations in the transparency of the regions of the soundtrack allow varying intensities of light to reach the phototube. That's it. That's all we have. That's how sound is made at a movie theater. The region of the soundtrack that will allow the most current to be produced in the phototube. So light goes through right here. this region right here, and it gets converted to an electric current because it's hitting a photoelectric surface. Electrons end up being ejected, right? The current's produced. Okay, and that ends up going to the speakers and making the sound. When do we have the highest current? In which region do we have the highest current produced? Which one would it be? 1, 2, 3, or 4? Who votes for 1? 2, 3, 4. Okay, and there's a few people that don't know. The answer is 3. Why would it be 3? Yep. Well, not a bright spot in terms of, interference, bright spot, dark spot, bright spot, dark spot. Like right here? Yeah. Okay, so more light will go through this, right? Because it's transparent, more transparent than the rest of them. If more light goes through, more photons go through, as long as we're above the threshold frequency, more photons will cause more electrons to be ejected, right? Now, photons are all the same, right? So the photons going through here, region 4, are also going to cause a current, just not as much, because you have less of them making it through. 121, the energy required to move an electron from the photoelectric surface is called the, quick, 5 seconds. What's the answer? B? Who says A? Who says B? The energy that's required to remove it is the work function. The minimum frequency is the threshold frequency. And finally, question number 122. In 1 second, this many photons are incident on a phototube. If each of these photons is greater than the threshold frequency, in other words, electrons will be ejected, then what's the current? It's a tough question. You guys remember from last unit? It's been a while now, but our last unit current was Q over T. Remember that? It's on your data sheet if you don't remember it, but we got to at least be familiar with it. We want to find current, charge over time. Well, the time's easy. It's 1 second. How do you find the charge? Well, if you have this many photons and they're all above the threshold frequency, then how many electrons do you have? That many electrons. So let's multiply 1.45 times 10 to the 6, 16, times the charge of an electron. That gives me my total charge. Plug that into there, and then we're going to solve for the current in amps. Make sense? Mathematically, it's easy, right? Conceptually, some of us probably would have struggled with that question to get to the answer.